have those at the expo, the baby expo at the Coliseum every year. They do.
Are you should enter your baby. I want to see that. I want to see a baby.
Okay, shh, ladies and gentlemen, here we go. I want to go ahead and get started. Okay, we left off here yesterday, and I'm going to go ahead and bring around and give you some new notes. This is going to be on the back of page 2. Okay, so 3, 4, 5, 6, 7, 8. 1, 2, 3, 5, 6, 7, 8. Okay. Okay, so today we're going to kind of pick up where we left off as far as talking about distance, talking about displacement, talking about motion, okay? These words, distance, displacement, they probably don't mean a whole lot right now, but after today I hope that they do. So one of the things that I told you guys was going to be important was distance and time. And so today we're going to elaborate on this idea of distance. Yes, it does seem like it would be easy to... I have extras? Okay, thank you. It does seem like it would be easy to kind of talk about this thing called distance because you guys are like, oh, I know what distance is. Miles, feet, yards, I know how to measure. We've measured before. Not a big deal. But when we're talking about a way an object moves and its motion, there's a lot of changes in motion sometimes. And so we need to know what that looks like and how to talk about it in ways that make sense to physics. All right, so the first thing we need to understand is that we will be using meters and kilometers. These two units will be the cornerstone of our talk on distance. Okay? Meters for those things that happen kind of at our level, and kilometers if we're talking about very long distances. Unfortunately, in the United States, we have the great disadvantage of having two very popular measurement systems. We have the metric system, which, because we are a world power, we have to contend with and we have to use and recognize because it's what all of our science and our academic organizations use. But then we also have the American system, like miles, feet, yards, which also very prominent. I mean, it's prominent in all our sports and construction, etc., like that. So, whereas other countries can do everything in millimeters, centimeters, meters, etc., we have to do everything in both units, which means that in school we have to study how to convert from one to the other. If you haven't already picked up on it, these notes are fill in the blank, okay? So they're meant to be for you to follow along. Okay, shorter distances are measured in centimeters. Shorter distances are measured in centimeters. And what would be another unit that we could use for even smaller measurements? What did we think? Yeah, millimeters. Excellent. Or nanometers. We're going to talk about nanometers. Okay? It's very, 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 very small number. All right. Here's what I want you to do. You have a calculator. Here's a chart. I'm not going to walk you through the chart as an eighth grader. I want you to figure it out. I have put 5 conversions that I want done up on the board. I want you to use the chart and figure out how to convert these 5 things. I will tell you right now that half your test in about 3 to 4 weeks' time will be mathematical. So please start practicing now. If you don't have a calculator, wait for the person around you to use theirs, and then please borrow it. I will give you 2 minutes to complete this exercise starting now. Okay? All right, let's see how well you did, because we're getting close to our 2-minute mark. Let's just start with the first one, just to make sure we're all on the same page. How do I convert 12 inches to centimeters? How do I do that? Somebody? Bo? I would take the inches, 12, and I would multiply it according to this chart by 2.54. So what is 2.54 times 12, Miss Lalonde? 30.40. 30.40? Okay. Now, when we are working with conversions, your calculator may spit out a number that's got lots of decimal places. So a good rule of thumb, and you're going to see this on your test, and you're going to see this in class as we work with measurements, a good rule of thumb is to round your answers to something that's close to or as the number of digits the number you started with. Okay, so in this particular problem, if this I started with 12 inches, what would be a good number to round this to? Yeah. You can do 30.5 would be acceptable, or even 30. I will, for this purpose, I will do 30.5. So I would say that 12 inches is squiggly line equal sign 30.5 centimeters. What does the squiggly equal sign mean? What does it mean? Grace? About equal to. Actually, if you look in the back under the math symbols chart, it means approximately equal to, which is about equal to. Okay? It means that we get a little wiggle room. Hence, it's a wiggling equal sign. It's a wiggle sign, wiggle room. Okay? We have wiggle room here. It is not exact. Otherwise, it'd be the straight up equal sign. Yo. But it's not. It's a wavy sign. Okay? So it gives us a little bit of wiggle room. Now, what about 1 yard to meters? This one you probably didn't even need to do on a calculator. Yes, Grace. Mary.
0.91.
Sorry. 0.91. 1 yard. Approximately equal to 0.91 meters. Now, if I add 2 zeros to the yards, okay, really what have I done with the decimal? KC. I've moved it 2 places. Okay, so if I move this one 2 places, what's it become? Yeah, 91. There we go. Okay. What about miles to kilometers? Miles to kilometers. 5 miles to kilometers. What did I have to multiply by here? Isabella?
You have to multiply 5 times 0.9.
No. Miles to kilometers.
1.6 kilometers.
5 times 1.61, which is approximately how many kilometers? Yeah. 8.05. We will say approximately 8 kilometers. And then last but not least, 492 kilometers is equal to approximately how many miles? Bo?
305.
Yeah, approximately 305 miles. Okay, where this would be useful to you, even if you were never in a scientific field. If you go overseas, or even to Canada or Mexico, there's speed limit signs, any vehicles over there, any of their signs whatsoever are in kilometers.
Why don't they just change it?
Well, because they're on board with the rest of the world. We're the ones that are different. So, if you go into Canada, you'll see signs for Toronto, hundreds of kilometers away, basically. So if I saw, let's say Toronto was 492 kilometers away, that would mean that it's roughly 300 miles. Okay? This looks way bigger than it really is. Our brains think in miles because since we were very little, we've been talking about distances in feet, inches, miles, yards, etc. Our brain processes this because it's been trained to process this. Kilometers doesn't have any, there's no pieces of our brain that really are in sync with meters and kilometers. If someone said 1,000 kilometers, I couldn't give you an example of something 1,000 kilometers away. If someone said 100 miles, I could probably give you an approximation of something 100 miles away. My brain thinks in miles. Mr. Miller.
Did you have a car that way?
I had a van that was in kilometers, yeah. My odometer, which reads how far my van has traveled, was also in kilometers. So when I went to sell it, I had to tell the people that yes, even though it says like 160,000, okay, it doesn't actually have that many miles because it's in kilometers. Okay, so that's where you have to be careful. If you're going to buy a vehicle in Canada, you better make sure that it is the American equivalent, or otherwise it's going to look like it's got way more wear and tear. Because kilometers is always going to be a bigger number than miles. Miles is a bigger unit than a kilometer. Here in the United States, we actually use kilometers. Drake, what is something you could do that is based in kilometers? Point out Drake for a very specific reason.
Cross country.
Cross country. They measure, like what's an example of a race you could do? A 3K, 3 kilometers. Or a 5K, 5 kilometers. 10K. 10 kilometers. Okay? So these are examples of what it would be like to use kilometers here in America. Okay? Here's the deal about this chart. If you pay attention and ask good questions in class, I'll give you the chart for your test. If you don't pay attention and don't ask good questions, I will make you memorize it. So in this class, I'm not usually struggling for good questions. This class usually asks very good questions. So I'm not worried about it in here. But it's the same policy across the board. All right, let's move on. Here's what I need. Your packets have this similar chart. However, it's dark and it's not easy to read, and we're going to be making a lot of notes on it. As a matter of fact, the rest of our notes are going to be based off this chart. So, if you turn to the very back of your packet, there's a blank page on the very back. I recommend taking a couple minutes, recreate this image on the very back of your notes. Okay? Please include all the information that you see, because we're going to use it all today. Okay, let's go ahead. As you're drawing, I'm going to just walk through some things here. I'm going to ask some questions. Feel free to take your time, okay, because this drawing, believe it or not, while it's very simple, is also quite important. Okay. First of all, we have a person that's walking on a field, and this person starts where? Where are they starting? Yeah, the start line. Very good. Okay, very good. Do they finish at the finish line, though? No, they do not. So there's one thing that we have to be aware of. They do not finish at the finish line. Okay, so there's something we have to consider. All right, so we know they start at the start line. They do not finish at the finish line. And how do we know that? What kind of symbolism are they using to describe or show us how this, and this is a woman, by the way, according to your notes, how she moved? Lalonde? An arrow! Ladies and gentlemen, I love arrows. Arrows are fantastic. That way, nope. That way, nope. Up, nope. Down, nope. That way, nope. That way. Arrows are fantastic. Green arrows, yellow arrows, red arrows, left arrows, right arrows, straight, turn around, swervy road, roundabout. Okay, the arrows are fantastic. They tell us so much information. Could you imagine life without arrows? No deer hunting. Okay, no Cupid. No arrows. No pointiness. Okay, no arrows.
What about those things when you're like in a curve like playhouses?
That's right. You know, what if you're on a road and there's arrows that show you that the road's going to like be all swervy, and so you don't know that, so you keep going, and then sudden, oh, it swerves, and you keep going straight. There was no arrow to tell you to turn. Okay?
Shouldn't you be a careful driver and know not to?
Some people need literal interpretation. Yep. There's an episode of The Office. I don't know how many of you ever watched the episode,
I love the
where
Office.
the one guy is listening to his GPS and it tells him to turn, and he's like, I've got to listen to my GPS, and he turns and he drives his car right into a lake. Okay?
I saw that. I remember when
So-
I liked seeing if the baby stroller was indestructible.
Okay, so here's what we got going on. We have an arrow. That's important. Tells us or shows us where this woman has walked or jogged, etc. Okay, now what about these markers on the side? Okay, what do they tell us? Yeah. Okay, they're in meters. That's important. So this is not a football field, even though it kind of has a similar layout or structure, right? Football fields usually are kind of green unless it's a team that has a special field that's a different color. It has markers that are spaced at intervals of 10, okay? But unlike a football field, this is in meters, for one, and it only goes from 0 to 50. Okay, so it's a little different. So that's something we have to take into consideration. All right, I'm going to ask an initial question just to kind of get us thinking about this. The woman is currently on which meter line? Yes. The 20-meter line. So she's standing on the 20-meter line. So could I make the argument that she's only gone 20 meters?
No.
Why not? She's on the 20-meter line. Didn't she go 20 meters? Yeah.
Because the arrow says she went down. She went all the way across the line.
So the meter lines don't tell me how far she went. So what are they then? What good are they if they don't tell me how far she went?
Because then
Because you're right on, Caitlin, by the way. Yes. What good are these meter lines? Jacob?
Because then you know how, once you add it all up, then you're not done.
Okay. So once I add it all up, then because I can add it up because I know the spacing, that would be helpful. There's something points that these can kind of be labeled as. Okay, we talked about them yesterday. When you're measuring a change in an object's position, so like this person, we're measuring her change in position. We are referring to or looking at these numbers. They're called what? They're called reference points. So if we look at the 0, 10, 20, 30, 40, 50 meter line, we know exactly, because Mr. Parnan said so, we know how far she's gone because we keep referencing these meter lines. They're there for reference. The same thing in a football game. In a football game, you might move the ball 5 yards. You might go from the 40 to the 45. Okay? And obviously you could do that on either end of the field. All right, so because I go from the 40 to the 45, does that mean I traveled 45 yards? No, doesn't mean that at all. It means that I went from reference point 40 to reference point 45. Okay, there's a difference there. So here we see that she's going from reference point 0 to reference point 50 and then to reference point 20. Okay, and so what we've been charged with here is trying to figure out what kinds of information can we gather from this. So, Mr. Chanceloy, what would you say her total distance traveled was? Not start to finish, because that would be a misnomer. Bad wording on my part. Let's say from the time she started to where she ended up would be a better way to say it. How many meters did she travel total? How many do you think? Total distance traveled. I'll give you a minute. Go ahead. 80. Okay, how do we know? Somebody walk me through it. Land?
All the markers.
Okay, so she starts the start line and goes how far in one direction? Jacob. She goes 50, okay? So she starts at the 0 and goes to the 50. So if I go over here, 0 here, 50 here. Now, does she then veer off and go to the bathroom, get a drink, and then come back? No, the arrow tells me she does a 180-degree turn and goes back the way she came. How far? Yeah, 30 meters. Okay, so she went 10, 20, 30, 40, 50 in this direction, does an about face, and goes back 10, 20, 30. 50 plus 30. Oh, you're getting all tricky biz on me now. Tricky biz. No. You're about face. You know, like back. Okay? Even though it doesn't do a very good representation. But yes, you technically would be right. We're not going to be that finicky. MP. Okay? All right. GP. Here's what I need. I need you to tell me how far she is from where she started. She's 20 meters. Okay, so this is called displacement. I want you to, on your diagram, right near the 20 meter mark, just put the word displacement. D-I-S-P-L-A-C-E-M-E-N-T. Displacement. And she is indeed 20 meters from where she started. How are these two things different, besides obviously having different numbers? Why total distance traveled versus displacement? How are they different? Caitlin?
Because the total distance she traveled is what she walked, and displacement is how far she has to go.
Okay. What she walked, I'm going to call that the path, capital P-A-T-H. Okay, the path. All right, so if I'm going to the store, how far I walk depends on which route I take. If I go straight there, that's a shorter distance than if I decide to go, make a right, go down a mile, make a left, go down, visit a friend for a little bit, go back out, go down a little bit more. Oh, I forgot something, go all the way back home. Then I go leave again and go to the store. Okay? I'm going to walk a lot more. My total distance traveled is going to be greater because my path is longer. However, if I go to the store by taking the long way, or if I go to the store by taking the short way, it doesn't matter. If I go to the store, I'm at the store. That's what we call displacement. Okay? Displacement is your distance from your starting point. Okay? Your distance from your starting point. So let's say that each and every day I go from my house to work. Okay? I start at my house and I go to work. I go 4.1 miles to work. Okay? Roughly, we'll just assume we'll round to 4. Okay? So when I'm at work, what is my displacement from home? Yeah. 4 miles. Now, I leave, I go to work. My displacement is 4 miles. I go back home. When I get home, what is my new displacement? 0. Because I'm right where I started. If she walked 20 more meters, her displacement would be 0. Because she'd be 0 distance from her starting point. Okay, now, let's say for a moment that I leave my house, go to work, have to go back home, come to work. Oh, I forgot something. Go back home, come to work. I go back home. What's my displacement? Yeah. 0. Did I travel a lot, though? Yeah, I traveled a grand total of 32 miles, according to my calculation, because I went back and forth 4 times. So I could go 32 miles, and according to displacement, it would look like 0. These two things are not the same. Distance traveled and displacement are not the same. All right, let's look at what these notes have to say. Suppose the runner jogs 50 meters, then turns around and runs back to the 20-meter mark. The runner travels 50 meters in the original direction. Ignore the north, ignore the south. You may cross those out in your notes if you so choose. They are not correct. I have to fix those. So the total distance she went, total distance traveled, is 80 meters. So, Caleb, thank you. You were correct. Now, I think you might have gotten some help, correct?
Yeah,
maybe.
I didn't know where she started.
Oh, yeah, the start line. Very finicky. You really got very elusive.
How do you know where to start at finish line?
Because my arrow. All right, now, sometimes you may want to not only know your distance, so the distance traveled, but how far you are from a reference point, in this case, the start line. This idea is called displacement, and we kind of talked through that a little bit already.
Displacement. Distance and direction of an object's change in position from the starting point.
Yeah, that. Yep. Okay.
Displacement.
Distance and direction of an object change in position from the starting point.
That is definitely you.
Okay, that's Shanana, Siri's cousin. Okay, and the displacement is always in reference, usually to the starting point, but really to the reference point, whatever I set that as. All right, this is very common. You've used this before probably. Think of GPS. When you put an address into a GPS, what are you giving the GPS? Yeah, a reference point. So then the GPS tells you not only how long it takes to get there, but what the distance is. Displacement. Now, when I'm in the GPS, when I'm driving and the GPS is going off, I might, in theory, go really far and then go back and then go really far and then, I might have to stop off. Well, then I forgot something. I go back home and I go back. The whole time the GPS keeps telling me my distance from my reference point. Okay? It doesn't tell me how far I've traveled overall. There is something on our car that does that, though. What is the little thing, and I said it earlier today, what is the thing in our car that measures how far we've traveled total? Yeah. Not a pedometer, that measures our steps. Okay? Yeah. An odometer. Yes. An odometer.
Dad, you look like an Irish guy.
An Irish guy?
Ew.
Okay, so an odometer measures how far we go total. And in the United States, it measures it in miles, and in other foreign countries, it measures it in kilometers. Okay, so needless to say, our total distance traveled is measured by our vehicles. Okay, and usually GPS is more focused on displacement because we don't care how far we're traveling usually. Okay, we really want to know just like how far we are from where we want to be or how far we are from where we came. That's really what we want to know. If we plan a trip, we don't measure it, and we usually measure it how many miles it is away from our house. We're looking at displacement. Okay, so yeah, just trying to go over the checklist in my head of things I need to talk about today. All right, the length of the runner's displacement and the distance traveled would be the same if they're in a straight line. Okay, but as soon as the person turns, they become different values. Okay, I'm going to give you an example of distance and total distance traveled and displacement. And I'm going to do this by erasing a few of these. Okay, let's say we have a house. Okay, and put a little door in the house here. Maybe a window. Okay, so here's my house. And what I'm going to decide to do is I'm going to go to the grocery store. So over here is the grocery store. Okay? And it's a triangular grocery store. Or more like a cone. Okay, now I've decided that the distance to the grocery store is 2 miles. I'm up for a nice walk. So I leave the house, okay, and as I go through this, I'm going to put the different things that I'm doing, the different distances I travel as markers. So position 1, position 2, position 3, position 4, etc. So I leave the house and I go about 1/4 of the way. Okay, so I'm walking along, singing my song, doing my jig. Okay? Doing my jig, and I realize, oops. Okay, position 1. I forgot something. Okay? So position 1 is, I get about 1/4 of the way, I go, oops, I have to go back home. Position 2, I'm at home. I had to pick up what I left. Okay? Then position 3 is, I make it 3/4 of the way. Okay, so I'm really going along now, singing my song. Okay, power walking. Okay, and I realize I get a phone call. Okay, so I've got little notes here. Okay, and I realize this is point 3. A friend of mine wants me to pick him up and then walk him to the store as well. Except that my friend lives in a box the other direction from my house. So I have to go all the way back. This is going to be position 4. I pick up my friend. My friend lives 1 mile from my house in the other direction. Okay, so first position, I should say, is I start at the house, I go here. Then I go back to the house. Then I go forward. Then I go back to here. Then I am going to go all the way to the grocery store, position 5. And I'm going to go back home, position 6. And I'm going to put the star here as this is where I started. Okay, now we're going to walk through this together. First of all, what is my displacement? Okay, let's look at the definition of displacement. Your distance from your starting point. So I start here, I go here, I go back, I go here, I go here, I go here, I go here. What is my displacement? 0 meters. So at the end of the day, if I look at just displacement, I didn't go anywhere. Cool. Now, yes, GP. You mean I should be measuring it in meters instead of miles?
No, I thought the whole time you said you were going in miles. So.
Well, it is in miles. Oh! Thank you for catching that. Thank you very much. Okay? Yeah, you were totally right. Okay, but now I really need to know, what is my total distance traveled? Okay, let's walk through this. We start here, we go a half mile, because it's a quarter of the way. So we go 0.5 miles for the first leg of the trip. Okay, then we have to go back home. That's another half mile. Then we go here. How far is that? Yeah. It is. It's yes, it is. It's 1.5 miles. Okay? And then we have to go where? Mary? To my friend in the box. Okay? So I go 1.5 back and an additional one. So that is how much? 2.5 miles. Okay? Then I go all the way from the box to the store, which is a grand total of 3 miles. And then I go from the store back home. That's 2 miles. So that's 1, 5, because 1 plus 1.5 is 2.5, 2.5, 2.5 is 5, plus 3 is 8, plus 2. So this whole process, I went 10 miles.
That was a big exercise.
10 miles. All I wanted to do was go to the store. But I forgot something, then my phone rings, and I got to go visit my friend in the box friend. Then we go, box friend and I go to the GS, then the GS home, okay? And maybe our friend was GP. GP in a box, GP and I went to the GS, and then we went home, okay? Yeah, well, yes.
How did the box person figure out that you were going to the store exactly?
That's true. Surveillance.
That's kind of
So
creepy.
then the box is Elena.
Well, I mean, they live in a box. What do you expect?
How can he
That's
have
true.
surveillance when he lives in just a box?
Oh, he spends all his money on surveillance so that he ends up having to live in a box.
What if he has
He has an awesome camera equipment, but he lives in a box. Now, granted,
That's Elena.
you know.
How does he get the power?
All right. Shh. So, do you get, stop real quick because we're almost out of time. Do you get the idea here? Total distance and displacement are different. Now, let's say for a moment that I had stopped at number 1. What would have been my displacement? 0.5 miles. Okay? Let's say I had stopped at 4. What would have been my displacement? 1 mile. Here's the problem. How do I know in which direction? I don't. Right now I don't. So here's what I have to, the last thing I want you to write down in your notes today. Displacement requires direction. I'm going to add this over here. This requires direction. There's a lot of ways we can do direction. I'll do it this way. This is east. This is west. So if they had stopped here, this would have been 0.5 miles east. If they had stopped over here, this would have been 1 mile, what? West. Exactly. So distance will play an important role. And that makes sense. If we don't specify direction, in theory, there's more than one way then to describe it. I'll give you an example. Caleb decides that he's going to tell his mom he's going to go to the store. And instead of telling her which store, he says, oh, it's only a mile away. In theory, there are several options. If this is Caleb's house from the view, he can literally visit any store within a 1 mile what? Radius. And if we lived in the futuristic time, then anything 1 mile above his house would count too. Maybe there's a floating store up there. Okay? Anything within a mile of his house, up, down, maybe it's a store in the ground. Okay? He went down or he's going to a mine. He's going to the miner's store. Guy's got to pick up his hard hat and his pickaxe. Okay? It doesn't matter. anywhere within a mile of his house, up, down, left, right, there, back, and again, it doesn't matter, is within a mile. We have to specify direction, otherwise it's open to interpretation. And that's it for today. Ladies and gentlemen, you are free to go. Have a great afternoon, no homework.
I think I'll go to the line. Good investment.
A good investment.
There's